Well, folks, we're actually drawing close to July 4th and afterwards. So there's a nice summer song. Here we are. This is one way to spend your summer here inside. In fact, let's put some light on the situation. It's a little cloudy today. Boom. Oh, my goodness, there's some light. So today we're actually going to talk about things that you might throw around in a park, projectiles. It could be a baseball that's been struck, a tennis ball. You could be shooting some basketball, playing against some friends. You could be maybe throwing some frisbee around, etc., some ultimate. Whatever it happens to be, projectiles follow some laws of motion. We're going to get into Newton's laws of motion and the law of gravity here in a bit. But this is kind of the last part of the kinematic section. So this is going to be a fairly short lecture, I think, I hope. And it's going to focus on the effect of gravity on projectiles. And then we're going to throw in some wind drag, fluid drag, and that's a type of force. So that's going to, I think, dovetail into our discussion about forces, etc. So without further ado, we'll get started. Okay, so projectiles, they're basically things you can throw, and they're no longer either in contact with a baseball bat or a tennis racket or anything else. There we go. So there's a projectile right there. If you look real fast, that's a softball. So they're under the influence of gravity and sometimes wind drag. We're going to take into account gravity first of all. So the type of flight for a projectile is called a trajectory. If we assume no air drag, it follows a path we know as a parabola. So here we see someone shooting a jump shot. Let's see, 8 meters. That's pretty long. Okay. So that's about a 26-footer. So that's definitely a 3-pointer. That's way out there. So maybe that's Seth Curry going to shoot his shot. There's the initial velocity vector that's drawn almost correctly. Maybe what we'll say is he's putting a bit of backspin on it. The backspin is actually going to create a little bit of lift. So as time goes on, we're going to talk about how spinning objects, like a spinning softball or a baseball, can actually create a force that causes it to curve, either down or sideways. In the case of a basketball or a golf ball that has backspin on it, it actually causes it to rise a bit. Not so much with a basketball, because basketball is not thrown with a great deal of velocity, and the backspin isn't quite great enough to create a very large force. If you kick a soccer ball and put like a side spin or a top spin or a backspin on it, then you can produce a significant amount of curvature. Okay, so we'll assume gravity is the only thing acting on it. So is a projectile is an object. This could even be a person. This could be someone doing the high jump or the long jump. This projectile, as it's moving, if we resolve the vector, so one of the things that we talked about in one of the lectures that you'll see are vector composition and vector resolution. If we resolve this vector into horizontal and vertical components, that vertical component changes at a constant rate due to the fact that gravity acts at a constant rate, 9.81 meters per second squared of acceleration. And in the case of the English system, it's 32 feet per second squared. Okay, so whether it's a basketball or whether it's, as I'm looking at this, it probably should drop a little bit sharper than it leaves his hand, believe it or not. And that's because as the basketball moves on, it actually slows down a little bit due to wind drag. So like if a ball's hit to the outfield because of wind drag, the ball is going to descend at a steeper angle than when you hit it. So you might hit it at like a 50 or 60 degree angle. It could come down at like a 70, 80 degree angle, probably more like a 70, 75 degree angle. So if you've ever played the outfield in softball or baseball, it always seems like that ball's coming down at a real steep angle, and wherever the sun happens to be up in the sky, that's where it's coming from. So remember that at all times when you're in the outfield, expect that. There we go. So projectile motion, what we're going to be doing is talking about things like projectile height, projectile speed, and projectile angle. Projectile speed and projectile angle are basically the two components of the velocity vector. That's going to change over time because gravity is going to have a constant effect. Projectile height also alters the optimal projectile angle. That's the angle between horizontal and where the projection is going. So you might want maybe a steeper shot, especially if you want accuracy, like a basketball shot. So this angle definitely needs to be greater than 45 degrees, assuming this must be a very tall individual. That's 1 meter. That's a 3-foot high person. How tall is that goal? I didn't develop this myself, so this is always the fun part about getting. This is why I'm writing a book, my own book. Yeah, I'm trying to figure this out as I'm looking at it. That doesn't seem right. Okay, that's 3 meters. Should this be 1 meter? No, that doesn't seem like it. That person's probably 2 meters high, which would be around 6'2" or 6'3". That doesn't seem right. So the optimal projectile angle here should be probably about 50 degrees. That's kind of optimal for a free throw or a jump shot in basketball. So it should have a fairly high arc. If we take a look at, let's say, a shot by, and we may do this in just a second. I'm going to look this up as we're talking about it. Seth Curry, who is, of course, one of the great three-point shooters today, has won, I think, 5 NBA championships. I've almost lost track. I believe it is 5. So let's try this, see what I get. Jump shot. Shooting secrets. Okay, we're gonna watch him take a look at something. Okay, I'm gonna start it about right there. Hold on a second. I'm going to pause. Okay, let's take a look at a shot or two. Here's Seth Curry with the ball. I missed that one. Come on, Seth. Okay, so you can see this is a pretty steep angle here. And if you're looking at, and that could be like a 55, 60 degree angle, he's moved up a little bit. Can't quite freeze frame with YouTube's disadvantages. This gives us a pretty good, his hands were about right here with release. So that's about a 50, close to 55 degrees. That's a pretty good angle. What that's going to allow the basketball to do, and he's going to put some backspin on it, which actually makes it more stable in the air. So we're going to talk in a little bit about angular momentum. That'll be in a few lectures. And with angular momentum, you have a ball that's spinning around an axis. So you have something called a right-hand rule. Your fingers represent the spin of the ball. The thumb is the axis of rotation. As a ball spins, it increases its angular momentum. And that actually makes the object more stable in the air up until the point where the rotation speed or angular velocity is so high, it actually starts to create a pressure difference if you have a rough surface like the seams of a ball or a soccer ball or felt on a tennis ball. So in this case, it's actually going to stabilize the ball in the air. That's one of the advantages of a backspin. Also, when it hits the rim, it's more likely that because of the backspin to slow down, and that with that bounce, it has a better chance of going into the basket, even if it's not a perfect shot. So this is about a 55-degree angle. Oh, he missed it. Come on, Seth. I just clicked on this randomly, so I'm getting burned right here. Come on, Seth. Do it for me. Hit it. There we go. Okay. Get out while we can. So hold on a second. And we're back. So if it's Seth Curry, could be, like I said, it could be a human. Sometimes humans are projectiles. Human cannonballs, for example, high jumpers, long jumpers, all kinds of examples. Look at your noise in the background. That's Trixie. Trixie's looking outside. There's someone walking away. So hopefully there won't be too much barking. So projectile motion, the body's free of support. Again, one of the things you can see is someone's thrown a ball. And as we resolve that vector, split it into horizontal and vertical components, notice the magnitude of the vertical component changes, and it changes at a constant rate. That horizontal component, as long as we don't assume air drag, actually there's no change, believe it or not. So we're gonna look at a projectile. This was 2 or 3 years ago. Villanova, excuse me, versus North Carolina. This is the finals. In fact, this is the final shot. Tie game. Villanova is going to get the ball, and we're going to see their winning shot. So here we go. 3 seconds at midcourt. Gives it to Jenkins. Oh, is it going to go in? Yes, it is. That's always good for me. I went to Duke, so anytime I can watch UNC lose a game, it's a good thing. Especially national championship games. Oh, there's their bear. Let's look for the replay. Oh, a little slow-mo here. There's the pass. Oh, let's look at that again, because there's a number of things I want to look at. Oh, hold on. Faster now. He set. Oh, advertisements. Okay, watch. We don't want to say bend in biomechanics. We want to say flexed. Look at that. Knee flexion and hip flexion. He's getting into position. At this type of joint angle, the quadriceps, the plantar flexors, which are being stretched, the gluteus maximus and the hamstrings, the hip extensors, they're all being stretched. That's activating the stretch reflex. If you want to think about a muscle as a rubber band, I don't know if rubber bands around here somewhere, but imagine you have a rubber band and you're stretching that rubber band. The material properties of muscles are like a rubber band. You stretch them, they want to bounce back, but they're also activated. It's like having a rubber band with a motor built in. So when you stretch those muscles, the stretch reflex is going to increase force production by producing more cross bridges between actin and myosin. Stretching a muscle also increases calcium release, and when calcium binds to troponin C, it frees up the binding site between actin and myosin, so you get more cross bridges. The greater the number of cross bridges, if you imagine this is a myosin head, the more cross bridges between actin and myosin, they usually come in a pair, so I'm going to have 2 days here. The more cross bridges you have between actin and myosin, the greater the amount of force that can be produced. And the greater the turnover, the faster the muscle can contract. And so by flexing the knees, the ankle, it's really the dorsiflexion of the ankle, and flexion of the hip, it puts these muscles in a place where they're rapidly stretching. That means they can produce more force due to stretch reflex, calcium. You're also optimizing the number of cross bridges that can be formed. In other words, the binding sites that can bind to myosin heads is actually increased by stretching, by increasing the muscle length. In addition, the ability of those muscles to produce torque at the knee joint, the hip joint, the ankle are all increased. And so that means that that person's going to be able to jump higher and faster. Also, this is a great example of the kinematic chain, where we start with basically more central axes. So if you can imagine that this is a motor or a rocket, we're going to blast it off by preparing the plantar flexors of the ankle, extensors of the knee, extensors of the hip. We're going to see those movements first. As a matter of fact, you're probably going to see hip movement first, the knee movement, then at the ankle. Then you're going to see this movement at the shoulders. That's flexion, extension of the elbow, and finally wrist motion. So let's see, can't really go frame by frame with YouTube, but I'm going to try. So check that out. The knees are starting to extend now, starting to go up. The shoulders still aren't really moving that much. Now they are. We're getting into place. Oh yeah, there we go. Little kinematic chain. Starting to getting that rise in because we've got that hip extension, knee extension, plantar flexion right there. Want to get it above the defender. It's going to get a high release point. Check that out. Notice now the elbows extending, and finally the last thing we're going to see is that wrist flexion. So this is a true kinematic chain. You're going from more central axes to more peripheral axes, and that maximizes the velocity at the distal end. So that's indeed what we're going to see. There we go. So let's take a look at it from here. He catches it up. Look at that kinematic chain. It's released. Look at that backspin. There we go. Look at that backspin. High arc. The high arc gives you an advantage because that means that ball comes down towards the hoop, and it maximizes the probability that that ball can go through the hoop. So you need a relatively steep angle of the ball coming in. A flat angle, the ball is probably going to hit the front rim or the back rim, and it has a better chance of bouncing away. That's why with free throw shooting, you want to make sure you get enough arc with that free throw shot as well. That makes a difference in terms of accuracy. You probably notice a lot of centers, big guys in the NBA or college ball, will shoot a very flat shot. And in today's game, especially late in the game, it's hard to keep people like that in. Back in the day when Shaquille O'Neal was playing, they call it hack-a-shack. They would basically hack Shaquille O'Neal because he missed the free throws, and the other team would get the ball, and that would be a way of catching up. So that's a great example of projectile motion. Let's take a look at another one. Oh, this is going to be AC Law versus University of Kansas. And this is another game-winning shot. We saw one against University of Texas a while ago. This is another one against the University of Kansas back in the day when Billy Gillespie was the head coach, and actually Buzz Williams was the assistant coach. So let's check it out.
Another team's played the first pass really well. Double up. Hurt the extra pass.
Oh, it's a 201. I got to pay attention to directions. Let's do this. Okay.
It's an 8-point game.
So A&M was 8 points and 6 points behind. There's AC Law putting it in left-handed. The bank is open. They're within 4. Now within 2. He's going to take it. 26 seconds left. He gets that space. Left-handed jumper. Good for 3. A&M goes ahead by 1. Mr. Clutch!
Kansas timeout, 20 seconds to go. What a comeback by Law.
All right. I'll give away the ending. Aggies win. All right. So another good example of projectile motion. I like these examples. We need more. Oh, Randy Barnes. Here's another great one. This is the longest held record, I believe, in track and field. It is the shot put record held by Texas A&M graduate Randy Barnes, who's also won a gold medal in the 1996 Olympic Games in Atlanta. This is 1990 at UCLA. This is the world record for the men in the shot put. Let's check it out.
Second attempt for this particular, and just take a watch. Just take a look at what happened.
Watch the spinning rate.
Oh. Look at the extension.
So
Less than a minute to go.
wait. Let's take a look at this again. Oh. So we're going to start. Come on, advertisements, get out of the way.
Look at what happened.
So he's going to crouch down. Again, that's stretching those muscles, maximizing the amount of force. It also increases the amount of torque that the hip extensors, plantar flexors, knee extensors can produce, and therefore you get more force, more torque. And the other thing, this is a spin technique that starts with the shot putters back towards the target. He's going to build a lot of angular momentum, and that's going to turn into linear momentum as he thrusts this. It's a 16-pound shot, by the way. And as he moves forward, and he moves really rapidly, we're going to try to stop this at first to see how we do here. Frame by frame analysis. So he's going to start to rotate. And he's rotating so fast, it's hard to catch it. This is one of the shots I wanted y'all to look at. This is about a 35 to 38 degree angle. This is the optimal angle for launching that projectile. What you're trying to do is, or what he's trying to do with his dominant arm, is by leaning over like this, that means the movement that he's going to be producing at the shoulder is horizontal adduction. The reason that that is important is that maximizes the amount of muscle mass you're going to be able to use in the throw. So that means the entire pectoralis major, the sternal head, and the clavicular head. It also means we get the anterior deltoid muscle involved. If you tried to throw up like that, that's flexion. Only the clavicular heads of the pectoralis major is involved. So you have less muscle mass. The less muscle mass you have, the less force, the less power you're producing. So he's maximizing that as he's getting ready to throw it. And again, we get a kinematic chain because we start with trunk rotation, then we get shoulder movement, finally elbow extension before hurling it. And then he does something called a reverse, because he's spinning to slow down angular motion and his forward motion without fouling. So let's take a look at it again in regular speed. So one of the things about shot putters is they can produce, if you hear snoring in the background, that's Trixie. Okay. I put you to sleep. Oh my goodness. Well, hopefully you guys are still awake there. Trixie, wake up. There you go. Okay. There's a pop quiz later, Trixie, so be ready. So one of the things about shot putters, they're not only strong, they're big, they can produce a lot of force, but they can also do it quickly. And when we were talking about power before, we can think of it and derive it from work divided by time as the product of force you can exert times the velocity, how fast you can move. And so shot putters do both. What it means is that shot putters are true power athletes, and their fiber type composition is largely about 75% fast twitch and something like 20-25% slow twitch. So they have the fiber type distribution of a world-class sprinter. They're like a world-class sprinter. So a good linebacker in American football is also going to have a high percentage of fast twitch fibers. The same thing for a defensive end. So let's take a look at this again. This is the standing world record in the shot put. Boom.
that leap. He
There it
knew
is,
right
almost
away
out
he
of
was at or near
almost
world
out of their
record
court.
pace. The world mark told you yesterday. He
There it
thought
is, slow
he was in
motion.
shape.
Yeah, there's that optimal angle right there. Check it
He
out.
was in shape.
And that kinematic chain. And then he's going to do a reverse. He's going to switch his left leg for his right leg. The right leg's going to go in front of him, and it's going to create a force upward that actually tilts his body backwards and slows his forward momentum, and produces torque in the opposite direction of the movement. So what that does is that slows his body down, so he doesn't foul.
He says his weight is right now up to
There's a bar at the end of the circle, and if you cross that, then you foul. But in this case, he did not. So let's take a look at it again.
Second attempt for this particular.
Again, standing world record.
Just take a look at what happened. Less than a minute ago.
Boom.
Look at the extension.
30 years ago.
And look at that leap.
Just this April. So it's now 30 years and a couple months old. 30 years and actually a little over 2 months old. Unbelievable. So that's one of your Aggies that have won the gold medal in the shot put. The other one is another Randy, but not Randy Barnes. It's Randy Madsen, who I believe won 2 gold medals in the shot put. All right, I put Trixie to sleep again. Okay, so lots of examples of projectiles, footballs, javelins, discus. With the javelin, always watch out if you're especially a referee. In the 1988 Olympics in Seoul, Korea, one of the judges, and they wear these funny hats and coats, wasn't paying attention, and the javelin got him through the arm. So pay attention at all times. I hope that wasn't a world record throw, because, man, I'd be really mad if I were the javelin thrower. People can be projectiles. So a diver in swimming, a long jumper, triple jumper. It could be a golf shot. So lots of examples of projectiles. This is Bob Beamon, a really famous projectile, held the long jump record from 1968 to 1991. And he set it by 2 feet. This was up in Mexico City, you see 68 here, and that's 1968. It was at altitude. The air is a little thinner, and there's a little bit, gravity has a small amount less effect, but it only made an inch or so difference. It didn't really account for the world record. So he broke his personal best and the world record by over 2 feet. Over 2 feet. So pretty amazing. When we think about factors that affect the trajectory of a projectile and maybe kind of optimal throws in terms of angle and speed and height. If you're shooting a basketball shot, you don't want it to come up short. There'll be an air ball and everybody would laugh at you. You don't want it bouncing off the back rim. You want it just far enough. So you got to get the right angle, the right speed. The relative projection height can make a difference as well. The higher you release it, you can get away with a little flatter shot, not super flat, but it could be 50 degrees instead of 55 degrees. Here's someone throwing a baseball, and we're dividing these factors up into, it's really the projectile velocity. It's the combination of speed, that's the magnitude, and the angle. This ball's probably going to go over the catcher's head. Projectile height is the difference between where the ball is thrown or the object begins its path and where it finishes. So with a relative projectile height of 0, and if we assume no air drag, the optimal projectile angle for distance, and we call distance, horizontal distance, we call it range. It's like the range in golf. When people go out to the range, they may try to hit it a long way or hit it accurately. If the relative projection height is greater than 0, like the shot putter, the optimal projection angle is decreased. For a soccer ball that's kicked from the ground, if you want to kick it far, you probably should launch it at an angle close to 45 degrees. For a cannonball, about 45 degrees is optimal to maximize that distance, that range. If the relative projection height is greater than 0, like 2 meters high, a little over 6 feet, that would be for a shot putter, then that optimal projectile angle is going to be flatter for sure. If the relative projection height is going to be less than 0, so in other words, you're shooting up towards a target like in basketball, that increases the optimal projectile angle. So again, if the projection height is greater than 0, the optimal angle decreases. If it's less than 0, then the optimal angle increases. People work this out. Leonardo da Vinci, by the way, drew some classic figures with cannonballs years ago. Da Vinci used to work for the army, the military. That's why he got a hold of lots of cadavers and was able to look at the entire skeleton and muscles in the body. So obviously he had a lot of time on his hands when he wasn't doing master works of art. Adjusting this a little bit. Okay, let's cooperate here. There we go. So projection angle to maximize range and accuracy can be altered. As we mentioned with the shot put, you have a projection angle that's above 0, and you're also moving forward a little bit. That flattens that optimal angle to about 37 degrees. This is not very good technique. His shoulder should be roughly parallel with that optimal angle. For a basketball shot, this release, this one isn't bad. Doesn't completely look like Seth Curry, but pretty good. So this looks like it's in that 49 to 55 degree range. That's kind of optimal. For a long jumper, because you have a high forward speed, the projection angle is actually fairly flat. So this is the current world record holder in the long jump, Mike Powell, who set it in 1991. So I think this is the second longest world record in track. He set it at 8.95 meters. So it's, I think, 29 feet, about 4 inches. At that same meet, Carl Lewis actually set a world record, but there was wind at his back, and so they didn't count it. If the wind is blowing any more than 0.5 meters per second, that's just a few miles an hour, then it doesn't count. So Carl Lewis got rooked out. So the way we would calculate this with, for example, putting vectors together. And the thing about having to be able to jump something like 26 to 29 feet and beyond, you have to hit the board at sprinter speed. And I actually took this data from his world record jump, over 12 meters per second. That's really fast. That's almost as fast as Usain Bolt. Not quite, but doggone it, it's almost as fast. So that's why they run usually about 50, 60 meters, hit the board. When they hit the board, they're going to slow down their forward speed a little bit, and then they generate some upward speed using impulse. That's from Newton's second law, the law of acceleration. So his upward velocity, initial velocity, is 4.2 meters per second. So if we put these two vectors together, we're going to subtract, first of all, 3 vectors together. First of all, we're going to subtract that to 2.8 meters per second. That's in the opposite direction as the forward speed when it hits the board. So that's 9.4 meters per second. We got 4.2 meters per second on the other side. I just used tangent to be able to solve for this. And I get a 24.08 degree angle. And that's about what it was. It was about a 24 degree angle. I think Bob Beeman's angle was a little bit higher than that. So pretty amazing. He was able to generate a really high vertical velocity. Bob Beeman was. So when we go back to his long jump, he got way up in the air. I actually drew a basketball goal for fun. But the idea is he got a tremendous amount of height. Look at the distance between himself and the ground. And in contrast, Mike Powell got there with a lot of forward speed. He had to generate a lot of upward momentum, but he was running really super fast, basically sprinter speed fast. He was virtually as fast as Carl Lewis. Not quite, but almost as fast. So again, when we resolve the x and y vectors for projectile, that y vector is going to change at a constant rate, and the x vector doesn't change actually at all. So we can resolve the vector, and actually using some right triangle trigonometry, we can calculate, let's say for a ball that's thrown at 20 meters per second at an initial projectile angle of 40 degrees, we can calculate the x component using cosine, because the x component will be next to, or the vx side is going to be next to that 40-degree angle. So we can use cosine to solve for that. And the vertical component will be opposite that 40-degree angle. So we can use sine to solve for that. So pretty straightforward, I think, for the most part. Perpendicular vectors don't affect each other. What the heck does that mean? That means gravity can only affect the y component, can't affect the x component. Fluid drag can, but not gravity. Okay, so with gravity, you eventually get to the point, this gets interesting, where the wind drag or fluid drag, that force counteracts velocity, and you end up dropping at a constant speed. It's not good, because that constant speed is about 120 miles an hour. It's called terminal velocity. That means you're going to need a parachute. So a parachute hopefully will deploy. It will increase the fluid drag, so you become buoyant. It pushes you up, and that slows you down tremendously, so you can land without breaking your femur or tibia or a pelvic bone. Okay, so because gravity acts at a constant rate, we can use something called the equations of constant acceleration. The equations of constant acceleration. So for velocity in the vertical direction, or distance in the vertical direction, we have equations to solve for that. We can solve for the height of a projectile, like a football that's been punted. We can calculate the range. That's the distance that a ball or an object moves based on its initial velocity and its projectile angle. The main assumption here is that the projectile or the projectile height has to be equal to 0. There is a correction factor if the projection height is not 0. So I've got a little problem. Dave's kicking a soccer ball at 20 meters per second. If the projectile angle is 30 degrees, find the range. So we assume here that air drag is not significant. The projectile height is 0. So we can plug and chug this away. So the range is 2 times 20 meters per second squared. That's 400 meters squared per second squared. We'll divide by 9.81 meters per second squared, multiplied by the sine of 30 and by the cosine of 60 degrees. And there we go. And that gives me an answer of 3.51 meters, or 35.31 meters. That's actually pretty reasonable. So let's say goalies caught a ball, going to drop it on the ground, kick it forward at a projectile angle of about 30 degrees. 20 meters per second is a little over 40 miles an hour. So that's a pretty good kick. It's probably going to go not quite to midfield. So that's pretty typical, I think. Okay, so we add an air resistance. What does that do? Well, air resistance is going to knock down the trajectory of projectile. It's going to reduce the range, and you're also going to come in at a steep angle. So the reason that that happens is the direction of the force for fluid drag is always in the opposite direction versus the velocity vector of the ball or object at any point in time. So on the way up, wind drag is pushing down. That means it's going to reduce the apex or height, and pushing backwards, so it's going to reduce the range. When you get to the top of the parabola or the top of the trajectory, fluid drag is going to be in the opposite direction, so it's going to be completely backwards. So it's cutting way back on the range. But the cool thing is on the way down, it's pointing, sure, backwards, but also upwards. It's actually keeping the ball in the air for a little bit longer. So if you play baseball or softball and the ball's coming in from the out, getting hit towards the outfield, sometimes you notice when the ball's initially hit, it's going real fast. So a lot of people want to go back, and then they realize, oh, the ball slowed down a lot. The range is reduced, so I'm going to come forward. but then the ball stays in the air for a longer period of time, and it comes down at a really steep angle. So it's not uncommon for people who don't have a lot of experience to overcorrect not only once, but usually twice when the ball is hit. So it gets to be a little fun playing around with that. So again, reduced height of the apex with fluid drag, reduced range, and a steeper angle of descent. So this is true for a golf ball with hit with different clubs. So a driver, 3-iron, 6-iron, 9-iron, and they don't have a wedge, but a wedge might go. This is probably old school. People can, because of advances in equipment and because people do more resistor training, etc., most people can hit it a lot farther than they could 20, 30, 40, 50, 60 years ago. Improvements in club technology have made a big difference. So you've probably seen this golf club a time or two. There it is, titanium, basically shell, and a foam core. This produces a large elastic collision, and that ball goes a long, long way. And has a huge sweet spot compared to the old school persimmon wood. There you go. And then the early 80s technology, these were steelhead clubs. There we go. You can see the size is somewhere in the middle, right? So here's your evolution of the golf club from the persimmon wood to a steelhead, and finally a titanium alloy with foam insert on the inside. It's basically like corking a baseball bat or a softball bat. So you've heard maybe along the way some baseball players, not Barry Bonds, Sammy Sosa got caught corking a bat, trying to hit more home runs. That allows, when there's a collision between the baseball and the bat, it allows a more elastic collision. The ball bounces farther and therefore goes farther. If you're throwing a frisbee or a discus, pardon me, there we go. Here's one that Trixie hasn't chewed up yet. We use something called an angle of attack. So the frisbee is thrown like that, but you actually tilt it up as well as a discus. This angle of attack allows you to throw the frisbee, so when it goes up, a very small area of the frisbee collides with the air molecules. It's very aerodynamic. But on the way down, it acts like a glider. It maximizes the number of air molecules that are colliding with the bottom of the frisbee. So if you do this with a fan, that's an example of using fluid drag and maximizing the area or contact area that's exposed to the air molecules. What it means is we're pushing more air molecules out of the way if we do this versus that. That's not a very good fan. This is a much better fan. So small area exposed to those air molecules. You don't push that many air molecules out of the way. Here you push a lot of air molecules out of the way. So that's the idea, is we're turning the frisbee or discus into a glider over the last part of the throw. So there's your projection angle. The angle of attack means we're going to orient the long axis of the frisbee or discus just a little bit upwards. So let's take a look. I think I got, there we go. There's someone throwing the discus. Oh, look at that shoulder angle. That again is making sure that that dominant arm is producing horizontal adduction and not flexion. That maximizes the amount of force and therefore power in that throw. But notice that frisbee tilted up a little bit. See that angle of attack right there? That's going to keep it in the air for a little bit longer. And that optimal angle of attack is about 20 degrees or so, 18 to 22 degrees. It's going to maximize lift on the way down. I think I've got, let's see, you get kind of a glider effect. And let's see if this comes up. I think I'm going to have to, hold on a second. I think I had trouble embedding this. So just a second, and I'm going to pull up the YouTube video. Okay, we're back. Actually, the video that I had up had been taken down. That happens from time to time. So, but I was able to pull up the 2016 finals in the women's discus. So we're going to see, look at a couple of throws. The first one's really spectacular. We're going to get a couple of angles, a couple of looks at it. So let's check it out. First of all, you're going to see how fast they move. Secondly, one of the things to remember is that with the discus throw, the shot put technique that's used today, which is the spin technique, was developed from the discus technique. But what they did is, because the shot put weighs so much and it would have a large moment of inertia, that means resistance against angular motion. They put it against their neck when they rotate. With the discus, they want to hold it out on their fingertips. So that way, when they throw it, it actually creates some spin, and that stabilizes the discus in the air. So it gets, like when you throw a frisbee, you throw it with some spin on it. That spin helps to stabilize in the air, and you get, again, that glider effect with that angle of attack. So let's check it out here.
The 31st Olympiad, day 5 of competition here, and now the women's discus final. So we're away with a...
Hold on, let me try that again. Hold on a second. My frame got out of whack.
Here, and now
my apologies.
Women's
Here we go again.
Final.
Okay, so look how her back is facing towards the target. She's going to wind up, and that means she's going to put those muscles in a position where they can produce more force and more power. She's going to get a lot of trunk rotation into it. There's going to be a lot of trunk rotation, hip extension. She's going to use that kinematic chain, and really, because the arm gets to be outstretched, she's really going to generate a lot of not only angular velocity, but if you think about the discus as being on the outside of a circle, a large arc length, and therefore a greater curvilinear velocity. And then just using Newton's first law of motion, the law of inertia, when she lets it go, that inertia is carried through on that discus towards the target. And you're going to get to see big cage here, because a lot of stuff could happen. You don't want to get hit by a discus. Here we go. Oh, really nice wind up and good kinematic chain. Fantastic kinematic chain. So let's see. Going frame by frame is really hard. It's not really frame by frame, is it? Okay, let's go back. Let's watch this throw. And again, you can see how fast these folks are. They're large. They can produce a lot of force. But because of that speed, that product of force times velocity, that's power. So let's check it out. Faster and faster spin.
So
there it goes out.
With a yell and a scream. And as you can see,
that looked really cool.
So we're
the scream was helpful. Watch that discus when it's in the air. As it's coming down, notice that the discus is coming down like that. So we're maximizing the area that's exposed to the air molecules, and that means that we're maximizing fluid drag. So, and when we're done with this, I'm going to actually put up the fluid drag equation so that we can go through it, and so you'll see, I think, what's been done.
Scream, and as you can see,
it's almost 70 meters
on the
out.
monitors out beyond 65. That's a really good start for this lady. A PB of 66.28, so important.
Just well over 200 feet.
Get on the board. Let the emotion. 66.28, so important.
Oh, really good kinematic chain there. Check
really
it out
good
again.
Start for this lady. A PB of
really get that trunk rotation, shoulder, and then finally, wow.
To get one away early and get on
that
the board.
whip-like motion. Oh, check it out.
And
on the way up,
run away early and get on the board.
On the way up, notice it's kind of slicing right through the air. So perfect on the way up. We're only knocking a few air molecules out of the way. It's really aerodynamic, but on the way down, it becomes like a glider. And that allows it to stay in the air longer. Check it out. Oh my goodness, it's just
throw out past
keeps
the,
going.
65. People in the arena can't see that 65. It's superimposed digitally for us. Digitally for us. 65. It's superimposed digitally.
She did.
Very good throw out
so much
past
fun
the
here.
65.
Hold on a second. Oh yeah, look at this. So we're going to get to see that kinematic chain.
Arena.
Really nice there. Check that out. So you got the trunk ahead, and it's like a wound up spring. So the pectoralis major, anterior deltoid, the biceps, and the biceps actually can help with shoulder movement because the long head of the biceps crosses the shoulder joint as well as the elbow. So it is like a spring with a motor on it. So check it out. Oh my gosh, perfect. Oh, and look at that huge launch angle.
Superimposed digitally for us watching at home, but she'll be delighted with 65.52. That's
yeah, that's pretty good. So let's check out the next one. Oh my gosh, look at the stretch there.
from Cuba.
She's going to get a big stretch. Lots of flexibility. That's really going to help. The more flexibility you have, that allows that spring to be able to move the discus for a greater range of motion, longer period of time. That's basically a product of force times the amount of time it takes to be able to move that object. That's something we call impulse. That's the ability to change momentum. I'm going to write that down on a little whiteboard in just a second. Oh my goodness, the speed. A lot of power.
She'll be disappointed almost out to the edge of the sector.
I think it was a little bit too high.
Current world champion lets her first throw.
And it looked to me like
disappointed almost out to.
It was a little bit high. And when she gets near the edge here, she's going to back up. Maybe she was a little concerned about fouling. She kind of stopped that forward movement.
Current world champion lets her first
did get a nice
throw,
rotation,
and she'll be disappointed almost out to the edge of the sector.
Still really super impressive. So hang in there a second. We're going to pause that. Oops. So here we see an Aggie discus thrower getting herself towards that kinematic chain. Really, you can see you're generating a lot of force and power with her lower extremities and her torso. That's going to allow her to be able to throw it a long way. So we're going to come back here in just a second. Okay, we're back. We're going to focus on this equation here. This is the equation for fluid drag, just to explain a little bit what was going on with the discus, as well as it would work for a frisbee as well. So with that angle of attack, what we're doing is focusing on this little thing right here. This is called the area exposed that's normal or perpendicular to the air molecules. In the fluid drag equation, wind drag, air drag, water drag, etc., is the combination of something called the coefficient of drag. And that's how rough or smooth the surface is. The rougher a surface is, the more air drag it's going to create. The smoother it is, like a wing, the less air drag it's going to create. Low coefficient of drag creates something called laminar flow. That's kind of linear flow. If, like a big truck, if it creates turbulent flow, then the coefficient of drag gets larger. The area exposed, again, means the number of air molecules that you have to push out of the way. The air molecules push back. It's technically Newton's third law, the law of action and reaction. So on the way up, you're only pushing a few air molecules out of the way. Area that's exposed normal or perpendicular to the air molecules is decreased. But on the way down, remember they were maximizing that. So that means that this increases. R, that's actually should be rho. Let's go to symbol here. There we go. Rho, that's the density of the fluid. That means how dense the air is. So when you go to altitude and the air is less dense, then fluid drag is decreased. The last term is related to velocity. Technically, it's the relative velocity between airspeed and ground speed, but it means if a baseball is traveling faster, the faster it's traveling, the greater the effective fluid drag. When you're in your car, the faster it goes, the greater the effective fluid drag. And the amount of fluid drag is proportional to the square of that velocity. So if you go from 35 miles an hour to 70 miles an hour, the amount of fluid drag does double. It goes up 4 times, it quadruples. Okay, so in terms of the discus throw, let's see if I can move the discus person back and do that. Let's see if I can walk and chew gum at the same time.
It was not a great effort by her.
Good with a 64.81, but not.
Let's look at another throw. And you get, hopefully we'll get the idea.
Sandra Perkovic
Oh,
into
she
the
hit
net,
that.
though.
Oh, that wasn't good.
Perkovic into the net
She hit the
with her
netting.
opening throw. Look
So,
out.
the
These are
velocity
things that can
vector
play with your
direction's
mind. She
important,
was
folks. Boom.
in a
Oh
tough
my gosh.
qualifying session, very
All right.
good with a 64.81, but
Let's try
not
one more.
getting
Let's see what
around.
happens.
Who got it out there beyond 65. She'll want to bet.
Oh, she's going to keep it at a low angle. Let's see what's going to happen here.
Robert Michon, who got it out there beyond 65. She'll want to better that now. She's got the good one on the board.
Oh,
There's
look at
some
that
nice
spin.
height, and that's
Oh, it's
good.
out there,
That's maybe
65.
just below.
Just a
her
little bit
first
below
round
what
attempt,
she
but
did before.
really important. She looks to the coach saying, I was going to try something.
Let's look for someone else. Here we go.
At Perkovic, and we look at Caballero, and we look at the place, and she is firing up to throw a big one here.
Nina
She really
Caballero
does
from
need it.
Cuba.
She's under pressure. She's in the top 8, but there could be others who could knock her off the top 8
Take a look at one more.
position.
Against really flexible. I
You know,
thought
there's
that one's
others.
better.
There's 2 very good ladies still to come to get on the board.
Oh, that
She
was
needs
over
to produce, and
65.
she has.
Yes, she
Not
has. That's
quite
a very
enough
good effort
to
by
take the lead, but that was
Caballero.
pretty good. Hopefully they'll show her from that front angle. We'll see the kinematic link.
Cuban.
Oh, that's really good foot movement. And look at that angle. Probably just a little steep because that looks to be just a hair over 40 degrees. So maybe a little bit high. Oh, look at that.
That's 15 years of age.
Again,
That was 11 years ago.
turns it into a glider on the way down. So you get the idea. Okay, well, that does it for projectile motion. So our next discussion is going to be on force applications, then Newton's laws. Then we're going to talk about torque and torque applications. So have a good one, and we will see you guys soon.